Bioclass, we are going to go through these items for the end of cycle examinations.
For the wonder with Bioclass.
Item 1. A food poisoning outbreak is traced to a bacterial toxin that destroys the tight junctions between intestinal epithelial cells. This allows the toxin to enter the bloodstream. The toxin's mechanism is to act as a non-competitive inhibitor of succinate dehydrogenase, a crucial enzyme in both the Krebs cycle and the electron transport chain. Table: Systemic effects of the bacterial toxin. Quick analysis of the information. The toxin has two linked actions. 1, it destroys intestinal tight junctions, which allows the toxin to enter the blood. 2, once systemic, it non-competitively inhibits succinate dehydrogenase, an enzyme in the Krebs cycle and also complex 2 of the electron transport chain. The table shows high succinate in blood, low ATP and cramping in muscle, and reduced kidney filtration, all consistent with inhibited aerobic respiration and energy failure in cells that depend on it. Task. Part A. Explain the dual consequences of this toxin. First, how it breaches the body's primary epithelial barrier, and second, how its enzymatic inhibition disrupts the aerobic respiration system systemically. Part B. Propose strategies to manage this poisoning, addressing both the epithelial damage and the metabolic crisis. Part A. Barrier breach. Tight junctions seal gaps between intestinal epithelial cells and stop microbes or toxins from crossing. The bacterial toxin destroys tight junctions, causing loss of barrier function and local inflammation. With junctions gone, the toxin passes from the gut into the bloodstream. Systemic enzymatic inhibition. The toxin is a non-competitive inhibitor of succinate dehydrogenase, an enzyme in the Krebs cycle and also complex 2 of the electron transport chain. It binds to the enzyme at a site other than the active site and reduces the enzyme's activity even if the substrate, succinate, is present. Succinate accumulates in the blood. The Krebs cycle is slowed, fewer reduced carriers NADH and FADH2 are produced for the electron transport system. The ETC is disrupted at complex 2, so oxidative phosphorylation falls and ATP production drops. Cell and organ consequences. Muscle cells. Low ATP leads to impaired cross-bridge cycling and ion pumps, causing muscle weakness and cramping. Kidney tubule cells. These epithelial cells need ATP to run ion pumps and filtration processes. Energy deficiency leads to reduced filtration rate. Systemic effects. Cells shift to anaerobic glycolysis to make ATP, producing lactate, and organs that rely on high ATP, like the heart, brain, and kidneys, become dysfunctional. Part B. Strategies to manage the poisoning. Stop further toxin entry. This prevents more damage to the intestinal wall and stops more toxin from entering the bloodstream. Restore body fluids and circulation to replace what was lost and to help the kidneys remove the toxin. This improves blood flow, kidney function, and helps reduce the amount of toxins and succinate in the blood. Support energy production. Give a glucose solution to provide an alternative source of energy since aerobic respiration is blocked. This helps cells, especially muscles and kidneys, to keep working using anaerobic respiration until the toxin is cleared. Help damaged organs recover. Rest the muscles and allow the kidneys time to recover by keeping the body well hydrated. Treatment of cramps by gentle stretching and rehydration. Support intestinal healing with proper nutrition once the inflammation reduces. Prevent future poisoning. Ensure proper food hygiene. Cook and store foods safely to kill bacteria and prevent toxin production. Item 2. Farmers in Mbale, Mount Elgin Slopes, and Gulu, northern Uganda, reported contrasting yields of beans and sorghum. Beans thrive in Mbale but fail in Gulu, while sorghum thrives in Gulu but shows yellowing and stunted growth in Mbale. A student investigation compared environmental factors, leaf anatomy, and photosynthetic activity of these crops in the two districts. Farmers from Gulu recently attempted growing beans using irrigation, but yields remained low despite frequent watering. Quick analysis. Data show Mambale is cool at 20 degrees Celsius, wet, and at a high altitude of 1,600 meters. Crops there are C3, beans with low carbon dioxide uptake. Gulu is hot at 33 degrees Celsius, dry, and at a lower altitude of 900 meters. Dominant plants, sorghum, have C4 anatomy, crans, and high carbon dioxide uptake. These environmental plus physiological contrasts explain the different yields. Irrigation in Gulu occurred, but still yields remained low. Task. Part A. Assess why beans and sorghum show contrasting performance in Mambale and Gulu. Part B. Suggest strategies that could help improve the yield of beans in Gulu based on the physiological and anatomical characteristics of the plants. Different photosynthetic pathways, different temperatures, and water requirements. Beans C3 plants have no crans anatomy, enzymes rubisco fix carbon dioxide directly but favor cooler, moist conditions because at high temperatures, rubisco fixes oxygen, reducing net carbon gain. Sorghum is C4 plant, has crans anatomy. C4 anatomy concentrates carbon dioxide around rubisco, preventing photorespiration and sustaining high photosynthesis at high temperatures. Environmental match and mismatch for bean. Mambale, cool environment at 20 degrees Celsius, plus high rainfall, 1,500 millimeters, low photorespiration, and adequate water favor C3 beans, leading to high yield. Gulu, hot conditions around 33 degrees Celsius, plus low rainfall favor photorespiration and evaporative demand, disadvantaging C3 beans, but favoring C4 sorghum, whose enzymes work optimally at high temperatures. Physiological capacity, measured carbon dioxide uptake. Higher uptake in C4 plants, like sorghum, means greater carbon gain per unit leaf area under Gulu conditions, and sorghum grows better. Water relations and stomatal behavior implied by the environment. High temperature and low rainfall in Gulu increase evaporative demand. C3 plants close stomata to limit water loss. This reduces carbon dioxide entry and photosynthesis further. C4 plants maintain photosynthesis at lower stomatal opening, so they remain productive. Irrigation in Gulu failed to restore bean yields. Irrigation supplies water but does not lower leaf temperature or eliminate high photorespiration. At 33 degrees Celsius, beans still suffer heat stress and high photorespiration, stomatal behavior, heat damage to enzymes, or accelerated respiration offset the benefits of extra water. Thus, frequent watering alone is insufficient. Use heat and drought-tolerant or early maturing bean varieties. Varieties bred for higher temperature tolerance or faster life cycles avoid the hottest period and maintain rubisco activity longer. Microclimate modification, mulching and organic matter in soil, cooler soil, reduced evaporation, better water retention, stomata can stay open longer, and higher carbon dioxide uptake. Shade nets or agroforestry, partial shade from taller crops and trees, lower incident radiation and leaf temperature. This reduces photorespiration and heat stress, leading to improved bean photosynthesis. Optimize irrigation timing and method. Application of deeper, less frequent irrigation, early morning or late evening, to maintain soil moisture without causing midday stomatal closure cycles. Soil fertility and root health. Improved soil organic matter and supply balanced nitrogen and phosphorus. A vigorous plant with a good root system sustains higher transpiration and photosynthesis. Nutrients support enzyme systems, including rubisco, reducing stress impact. Alter planting time and spacing, planting to avoid the hottest months or increase plant density and row orientation to create mutual shade in midday. Integrated crop systems. Intercrop beans with taller sorghum or maize in a pattern that provides partial shade during the hottest hours.
Item 3. During the National Cross-Country Marathon held in Kapchorwa, 2,200 meters above sea level, 4 athletes, Joel, Brian, Lydia, and Mary, competed in a 15-kilometer race. Before the event, the weather was cold and dry. After the race, medical officers recorded the following data. Quick analysis. Captura is high, so inspired oxygen is lower. All athletes show exercise effects, increased heart rate, core temperature, and sweat, but Brian has the highest heart rate, highest core temperature, and highest sweat rate, with the lowest oxygen saturation and the highest white blood cell count. These linked observations point to severe cardiovascular and thermoregulatory strain, dehydration, and hypoxia-driven stress in Brian, explaining his dizziness and cramps. Task. Part A. Using the data, explain the physiological reasons for the observed differences in body temperature, heart rate, and oxygen saturation. Part B. Suggest strategies that could help Brian recover and maintain homeostasis after intense exercise at high altitude. Part A. Physiological reasons. Reduced oxygen availability at altitude, lower oxygen saturation. At 2,200 meters, atmospheric oxygen pressure is lower and arterial oxygen saturation falls under heavy exercise. Brian's oxygen saturation at 82%, the lowest among Joel's 90% and Mary's percent. Low oxygen in the blood reduces oxygen delivery to muscles. This causes a compensatory increase in heart rate to maintain oxygen delivery. When saturation drops, the cardiovascular system raises heart rate. Brian's heart rate, the highest, is a direct compensation for his low oxygen saturation. Joel and Mary had milder rises because their saturations were higher. Shift towards anaerobic metabolism leading to fatigue and cramps. Inadequate oxygen and very high muscular demand force muscles into partial anaerobic respiration, accumulation of lactic acid, and disruption of electrolyte balance. This promotes muscle cramps and dizziness, reduced cerebral perfusion. Thermoregulatory load and sweat loss. Exercise increases metabolic heat production. Brian's core temp was 39.8 degrees Celsius, the highest, and his sweat rate was 5.5, showing he produced more heat and perspired more. High sweat rate, large fluid, and electrolyte loss. Dehydration reduces stroke volume, further raising heart rate and dizziness. Loss of plasma volume from heavy sweating lowers venous return and stroke volume. Heart rate rises further to maintain cardiac output. Reduced circulating volume also lowers cerebral perfusion, leading to dizziness, faintness. Stress and inflammatory response. Elevated WBC in Brian's blood is consistent with physiological stress and exercise-induced leukocytosis and tissue stress. Others have lower WBCs, indicating less systemic stress. Other athletes, Joel, Mary, and Lydia, show more moderate heart rates, higher oxygen saturations, and lower core temperature plus sweat rates, indicating they paced better, had better acclimatization and fitness, lost less fluids and electrolytes, so they avoided a severe hypoxia and dehydration cascade. Stop exercising and lie down with legs elevated, which improves venous return and brain perfusion to reduce dizziness. Cool the body quickly, remove excess clothing, apply cool water to skin, or use a fan to lower core temperature. High core temp impairs recovery. Rehydrate with oral rehydration solution or electrolyte drink, replacing fluids and sodium and potassium ions lost in sweat to restore plasma volume and correct electrolyte imbalance causing cramps. Encourage slow and deep breathing, which improves alveolar ventilation and sometimes increases O2 saturation. If available and symptoms are severe, give supplemental oxygen. Stretch and gently massage cramped muscles after initial cooling and rehydration. Give a light carbohydrate snack to aid muscle recovery. Pacing and training. Train at altitude or simulate it. Race at a conservative pace to avoid exceeding aerobic capacity. Ensure good iron stores and carbohydrate availability for oxygen transport and aerobic metabolism. Warm-up and cooling strategies. An appropriate warm-up to prepare circulation and planned cooling to limit excessive core temperature rise.
Item 4.
During the National Mountain Marathon held in Kapchorwa, altitude 2,200 meters, 3 athletes, Peter, Sarah, and James, showed different endurance abilities. All were trained for 3 months under distinct environmental conditions before the event. Peter trained at sea level in Tubby. Sarah trained in Kapchorwa. James trained in Mabara, 1,400 meters, but recently recovered from mild carbon monoxide exposure after sleeping near a charcoal stove. Before and after the race, physiological data were recorded. Quick analysis. Race at 2,200 meters gives reduced inspired oxygen. Sarah trained at that altitude and shows the best physiological profile: high hemoglobin, low post-race heart rate, and fastest recovery. Peter trained at sea level and performed second. James trained at a mid-altitude and recently had carbon monoxide exposure. He shows very low oxygen saturation, the highest heart rate and carbon dioxide, the lowest hemoglobin, and the longest recovery and collapsed. These facts explain performance differences. Sarah completed the race first, followed by Peter, while James collapsed and required oxygen therapy. Task. Part A. Explain the physiological reasons for the different performances among the 3 athletes. Part B. Suggest strategies that could help James improve his performance and recovery. Part A. Altitude and oxygen supply are the basic problems. At 2,200 meters, atmospheric oxygen partial pressure is lower, so less oxygen is available to the blood during heavy exercise. Athletes must increase ventilation and cardiac output to maintain oxygen delivery. Acclimatization by Sarah improved oxygen transport. Sarah had the highest hemoglobin level, more hemoglobin molecules to carry oxygen, better oxygen content in blood despite lower saturation. Her post-race heart rate, 120, the lowest of the 3, and recovery 3 minutes show efficient cardiovascular and ventilatory adaptation, greater stroke volume, and better oxygen extraction. These adaptations explain why she finished first. Sea-level training by Peter, partial disadvantage but preserved saturation. Peter trained at sea level. His oxygen saturation, 98%, is high due to a strong ventilatory response, but his hemoglobin level is lower than Sarah's, so his total oxygen content is less. To meet muscle oxygen demand, he raised his heart rate to 160 and took longer to recover, 10 minutes. This explains his second place, adequate oxygenation but less efficient altitude adaptation. Carbon monoxide exposure by James, major impairment of oxygen delivery. Carbon monoxide binds hemoglobin strongly, forming carboxyhemoglobin, reducing functional hemoglobin available and impairing oxygen release to tissues. James' hemoglobin level, lowest plus prior carbon monoxide exposure, explains his very low oxygen saturation and need for oxygen therapy. To compensate for poor oxygen delivery, his heart rate rose to 185, the highest, but compensation failed, leading to tissue hypoxia and collapse. His blood carbon dioxide concentration is highest, indicating hypoventilation or poor gas exchange and accumulation of metabolic carbon dioxide. Recovery time, 18 minutes, is prolonged because oxygen stores, hemoglobin function, and ventilation were impaired, and metabolic waste like lactate and carbon dioxide needed time to clear. Supplemental high-flow oxygen immediately displaces carbon monoxide from hemoglobin, increases dissolved oxygen, and speeds recovery of oxygen delivery. Avoid further carbon monoxide exposure, eliminate charcoal or stove exposure. Improve ventilation at home. Gradual return to activity only after medical clearance. Start with low-intensity aerobic sessions as symptoms and blood markers normalize. Nutrition to support hemoglobin recovery, iron, vitamin B12, and folate, adequate protein and calories to rebuild red cell mass. Altitude acclimatization program, spend progressive time at intermediate altitudes before competition to stimulate erythropoiesis, ventilatory drive, and capillary or mitochondrial changes. Monitor and optimize hemoglobin or iron status, regular blood tests. Treat iron deficiency promptly to avoid low hemoglobin limiting oxygen carriage.